All right, today we will deal with the transportation simplex. This is a new method that is only used for transportation problems, or you will see the variants anyway, but still this simplex is a specialized simplex, so it has some new steps in it. So for example, first of all, of course, we know that we have to balance the models. So we have a problem if it's unbalanced, if it has more supply or more demand than the other one, then we have to make sure that they are both equal to each other. Supply and demand should be equal to each other. So we first balance it, and then we find a starting solution, a basic feasible solution, using one of the methods we have seen so far, like the Vogel's method or the minimum cost or the northwest corner, or anything you can come up with, really. And then we assign a value u to each row and a value v to each column. Now, these will be used to calculate some cell values, let's call them for now, but they are actually your objective function coefficients. You can think of them like that, and you will use those coefficients to decide if the model is optimal or not. So if every value, every calculated value, as you can see, the value is calculated by u plus v minus c, if every value is less than 0 for the non-basic variables, then it's optimal. But if there's anything positive, then we keep doing iterations. Now, this part is, we know that the transportation simplex is a minimization simplex. This is how we are thinking about it in a normal way, because it's about cost minimization. We are trying to transport something from point A to point B, and we are trying to minimize the cost. As it's a minimization, we are trying to get rid of all the positive values in the objective function, positive coefficients in the objective function. So we are trying to make sure that everything is either 0 or negative. This is how we can take a look at it in a way. So if there's any positive value, if there's a positive coefficient, then we make a loop, we make an iteration, and then we recheck. We calculate the u and v values once more, and then check. So how do we pivot? How do we make the iteration? Now, we are trying to find a loop, and there will be only one possible loop in there. And when we find the loop, and you will see what I'm talking about soon, we will just make the iteration by making sure that the let's say there is a non-basic variable in there, and we are trying to turn it into a basic variable, which means that a basic variable will also leave the solution to make room for the non-basic variable. Okay, we always will have the same number of basic variables, which is the number of rows plus number of columns minus 1, as you remember. And to have that, when there is a non-basic variable becoming a basic variable and entering the solution, a basic variable should also leave the solution. So we're just trying to find who will leave the solution through that loop. So when we count those cells in the loop, and which means that only the corner cells, when you, let's say, graph a loop, when you draw a loop, you may go over basic variables as well, but they will not be part of the loop. To be part of the loop, you have to be on the corner of the loop. You will see what I'm talking about in the example clearly, but still, there is always an even number of corners. So there will always be either 4 corners or 6 or 8 or 10 or 12, whatever, but still there will always be an even number of corners in the loop. So that we know that when a non-basic variable is entering, a basic variable will leave the solution with it. So, for example, here is a solution, a basic feasible solution for the power plant question. Now, as you can see, our total supply is 35 for the first power plant, 50 for the second, and 40 for the third one. And the demands are 45, 20, 30, and 30 for cities 1 through 4. Now, this is just a basic solution. This is not the optimal solution yet. We have to make iterations to make it become an optimal one. First thing we have to do is find the values for u and v. Now, to find the values for u and v, you have to check the costs for basic variables and only basic variables. For example, over here, this is the first basic variable, which has a value of 35 and a cost of 8. Now, when we start finding values for u and v, we have to assume that one of them is 0. We can, by the way, we can give another value. It doesn't have to be 0, but it's a constant value, something that will be a pivot value for us. 0 is the easiest to calculate, so we usually give u1 0. Okay, you can give other values in here as well. It won't change the solution at all. Or you can give 0 to any other u or v value you want to. It won't change the solution at all. But still, usually we start with u1 is equal to 0. Because this is going to be a loop, so every u and v value will be dependent on each other. Okay, if you change any one of them, every other value will probably change with it as well. So this is 0. If u1 is 0, then v1 is going to be 8, because for each basic variable, its cost must be equal to the sum of its row and column values. So u1 is 0, so v1 has to be 8, because 0 plus 8 is 8. If v1 is 8, then u2 is going to be 1, because 8 plus 1 is 9. So this is another basic variable cost anyways. If u2 is 1, then v2 will be 11, because 1 plus 11 is 12. If u2 is 1, then v3 will be 12, because 1 plus 12 is 13. If v3 is 12, then u3 is 4. And if u3 is 4, then checking from here, v4 is 1. So we can find all the u and v values just using the costs of the current basic variables. Then we want to find the values for the non-basic variables. Now, the values we find here will be their coefficients. Okay, just remember, these are just like the objective function coefficients in the current solution. So what we need to do is we will add u and v values together and subtract the cost. So 0.0 plus 11 minus 6 is 5. 0.12 minus 10 is 2. 0.1 minus 9 is minus 8. And then we have here minus 5, 1 plus 1 minus 7. And over here is 6, 4 plus 11 minus 9. And over here is minus 2. So we have 6 here, 5, 2, minus 8, minus 5. Let's just go, yes. As you can see here, from here, we have some negative values which we want to see, and we have some positive values which we do not want to see. So we take the greatest positive, of course. This is a minimization, so we are trying to find the pivot place, which is going to be this one, okay, the greatest positive. So which means that this one over here, x32, so this x11, x12, x13, x14, etc., x32, this variable will become a basic variable. So we have to find the loop. Now, what is the loop? The loop is, for example, it might be a square, it might be a rectangle, it might be some kind of a butterfly shape, but it's something that has only corners and only straight lines. The corners will be, except this pivot point, will always be on a basic variable. For example, for this one, we start from here. Let's just try to draw it. And we start from this point, the pivot point, and we will try to go to any basic variable we can with a straight line. We cannot go diagonally. We cannot go like this shape, but we can go from here over here, or from here over here, or from here over here. So if I go from here to here, now from this point, I have to go to another basic variable, but there is no basic variable over here. So coming here was a mistake. I cannot go anywhere from there, so I cannot form a loop here. So let's just take this back. So I can just start here and go over here. Now, from here, I want to go to another basic variable, but I also want to make sure that this is a corner point. So I cannot go from here over here. From here, I can only go up. This is another basic variable. And from here, I can go either here or here. If I go over there, I can go over here as well. So as you can see, this is the pivot point. This is a corner point. This is the first basic variable, second basic variable, third basic variable, and fourth basic variable. And then I cannot go anywhere. There are no basic variables left to go. So this is not the right path. But I have gone over this basic variable. I could have used that one as well. So let's just go back and use that one instead. Now I can go back to my pivot point. As you can see, I have formed a rectangle or a square, doesn't really matter. But I have 4 corners, 1, 2, 3, 4. And each of them is on a basic variable or my pivot point. So this is my loop. This is my one and only loop over here. Using this loop, and let's just go to the next slide. And as you can see, it's more clear over here. Using this loop, I will make the iteration. Now, how can I make the iteration? Simple. When this one enters, Okay, think of it like this one. This non-basic variable will become a basic variable. Okay, and when this one enters, this cell will have a positive value. It will have a value. For example, I can say that, okay, this is going to be 5. Well, if this is 5, then my total here is going to be 25, 20 plus 5, and my total here is going to be 45. 5 plus 10 plus 30. But I don't want this one. I want it to be balanced. So if this is going to be 5, I have to subtract something from here and subtract something from here as well. So if this is going to be 5, this should be 15. It should go lower so as to keep the balance over here. And if this is going to be 5, this should become 5 as well. It should go lower so that the balance is kept over here. But if this one becomes 15, then the sum over here will change. It will become 45. And if this becomes 5, then the sum over here will change as well. It will become 25. So to compensate for that change, I should increase this value. This 20 will become 25. So what I have got here is actually, let's just write them. This one becomes 15. This one becomes 5. This one becomes 25. And this one becomes 5 as well. Now, 10 plus 15 plus 25, well, 50, no problems. 5, 15, 5, 0, 15, 5 is 20, no problems over here. 25 plus 5 is 30, no problems over here. 5 plus 5 plus 30 is 40, no problems over here. But if I make it like this, if I just increase this by 5, I will now have 1, 2, 3, 4, 5, 6, 7 basic variables, which is not feasible. I can only have 6 basic variables over here because I have a total of 7 rows or columns. Minus 1 is 6, so I should have 6 basic variables. So what I need to do is just find a solution, find a value here that will zero out one of the corner points. Now, let's say that this value is theta, and this theta will be calculated from here. Now, if this is theta, this value will become 10 minus theta because I want to keep the total 40. If this becomes 10 minus theta, this will become 20 minus theta, 20 plus theta. And if this becomes 20 plus theta, this will become 20 minus theta. You can think of it like this. For the corner of the new basic variable, that's the pivot point, we get a plus value. For its first neighbor, you get a minus value. For the second neighbor, a plus value. For the third neighbor, a minus value. For the fourth neighbor, a plus value, etc. So for each neighbor, it's a changing sign, plus, minus, etc. Now, as you can see here, plus theta, minus theta, plus theta, minus theta. Now, from here, I can just deduce that what I have to do is just get rid of one of those minus theta points so that it will become a 0. Now, to be able to do that, you have to pick one of those minus thetas and give the exact value that it has as its theta. So 10 minus theta can have a value of 10 for theta, so that we don't have a negative value. We cannot give 15 and make this negative. No, we cannot send negative goods. And 20 minus theta says that I can have a theta of 20. Now, I cannot have a theta of 20 because this would become a negative value. So theta can only be 20 at max. So, 10 at max. So theta is 10 over here. I know that this value will be 0 now. So if I give theta 10, this value, this cell will have a value of 10. This one becomes 10 as well. This will become 30, and this will become a 0 and leave the basis. Okay, it will never, it will no longer be a basic variable. Now it's a non-basic variable. So this is the current solution, the current feasible solution, but it's still not optimal. We don't know if it's optimal or not. So what we have to do is just recalculate the u and v values once more. So u1 is 0. This will become 8. This is 8. This will become 1. This is 1, 11. This is 11, 2. Now this is a change. So sorry, minus 2. And this is minus 2. So this will become 7, etc. As you can see, some things have changed. We have found new values. Why? Because our basic variables have changed. Let's go back. 0, 1, 4, 8, 11, 12, 1. 0, 1, minus 2. Instead of 4, we have minus 2 now. And instead of 1, we have 7 now. They have changed because this, let's go back a bit more. Over here, this was a basic variable. Now, this one is a basic variable. So how we calculate our u and v values have changed because the basic variable has moved. So these are our new basic variables. From here, we will calculate the values inside these cells once again. Their objective function coefficients, which you can see is 5. The most positive value over here is 5 now. And from here, I need to find a loop. Once again, I can see the loop clearly, easily here, because this is just like this one over here. Another square over here, 2 by 2. Simple. Now, this is the loop. So this will become a plus theta. This will become 10 minus theta, 10 plus theta, 35 minus theta. Once again, from 10 minus theta, the greatest value I can have is 10 for theta. So theta will be 10 over here, 25, 20, and this will leave the basis and become a 0. So this is the current feasible solution. Is it optimal? We don't know, we will see. We have to check the U and V values once more. So 0, 8, 1, 6, I guess. So 3 it would be, and 12 and 2. Yeah. Now, from here, we have to calculate those coefficients for non-basic variables once more. And we see that we still have one more positive value over here. So we will try to find a loop for this one. Now, when we try to find the loop for this one, once again, we start from this point and go to a basic variable. Now, here you have two ways. You can either go like this one, left, right, or up, down. Now, if I go to left, I have two options. If I go down, I only have one option. So I prefer to go down because one option is guaranteed to be in your loop. Okay. From two options, I could have gone to either of them and maybe made a mistake or take a longer route. I'm talking about bigger models, of course. From here, you can just see how to go and where to go. But still, if you have just one option to go, pick that one in a way. But think about it. If this was a basic variable as well, which would not happen easily, but still, if this one was a basic variable as well, you could have gone either 2 over here or 1 over here. You could have picked any one of them. It's still the same. This is not one by itself. Left and right are together. Up and down are together. So these over here are two options, but this is just one option over here. And from this one option, I can only go here. And from this one, I can only go there. There are no basic variables, neighboring basic variables for that one. And I go back here. Now my loop is a bit longer. And this basic variable is not a part of the loop. This is very important. This is not on a corner. Okay, this is just on the line. So this basic variable is not part of the loop. So it will not change at all. Only the corners change. Okay, the lines do not matter. Only the corners matter. So this is not going to be in the loop, and this will not change at all. So let's go to the next slide and see the loop from there as well. As you can see over here, this is the loop now. And from this loop, I will just add theta, minus theta, minus theta, and theta. And as you can see over here, 25 and 30, well, 25 is smaller. So theta will have a value of 25. And this is my current solution. And these are the U and V values for that one. And once we calculate all the objective function coefficients, or the reduced cost, as you can remember, and you can see that, okay, these are all negative. So this solution is optimal. Now, this is how the simplex works, okay? But there are some things that are very familiar. As I said, these are our objective function coefficients and our reduced cost as well. You can think of them like that. So we already know that how we can change these values, these costs, so that they can enter the solution, or they can at least create an alternative solution for the current one. So for example, if this 8 was reduced to 6, it might have entered the solution. Or if this 14 was reduced to 9, it might have entered the solution. It would become a 0 over here. So you could make a loop using this 0 as well. So this is the sensitivity analysis part. It's the same thing, almost the same thing with the normal simplex, but still there are a few quirks, of a few, let's say, different things that we can use over here. Now, first things first, changing the objective function coefficient of a non-basic variable. This is something we already know. And changing the objective function coefficient of a basic variable, this one we will have to go over. And increasing a single supply by theta or delta or whatever by delta, and a single demand by delta. Now, you can increase supply or a demand by itself, but it would imbalance the model. You don't want an imbalanced model, so you have to increase the supply and demand at the same time. We'll get there when we are going over that. But changing the coefficient of a non-basic variable in the objective function. Well, this is easy because we already know how this works, okay? We are just gonna calculate the blue values, and we know that they can only be equal to our reduced cost anyway. So we will just say that, okay, if you're gonna change something, how this will react? Well, these are simple. If this 9 was decreased to 2, it would have entered the solution. We already know that one. So this is nothing different from our usual reduce cost or allowable decrease functions. On the other hand, you can increase this value as much as you want. You can increase it by infinity, and it will still not be entering the solution because this is a minimization, and increasing the cost of a non-basic variable is useless. It will not enter the solution by increasing its cost. What about a basic variable? Now, this is a bit more trickier because when you increase or decrease, you can increase or decrease, you can go have it both ways. When you increase or decrease the cost of a basic variable, it might either leave the solution and let another non-basic variable enter instead of it, or it might force a basic variable to leave the solution. We remember that one, right? Think of it like this. It's a, let's say that there is a manufacturing plant or power production plant, and you are trying to decrease costs for a production method, and that method might make other methods obsolete. Okay, they might become useless because of the decreased cost of that method, and everything might be, every product might be produced by using that method anyways, or it might be a machine, or it might be some sort of, I don't know, a new technique, or hiring more stuff, etc. But still, if there is a change in the coefficient of a basic variable, it might have two different effects. It might make that basic variable leave the solution, or it might make that basic variable more important and make others leave the solution. That might go both ways, if you remember that one. Here, if we increase the value by delta over here, 6 plus delta, then our U and V values will change. Because if you remember from 10 minutes ago, all U and V values are calculated from the cost of the basic variable. So if I'm changing the cost of a basic variable, then my U and V values might change with it as well. So if this is delta over here, we start with 0, and this is the current basic variable on this row. So this is 6 plus delta, so this V value should become 6 plus delta as well. If this is 6 plus delta, over here is another basic variable. This is used to calculate. So 6 plus delta 9, oh, okay, this should be 3 minus delta. And if this is 3 minus delta, over here is 2 plus delta. Now, using these values, 3 minus delta, 6 plus delta, 2 minus delta, you can calculate all the coefficients for non-basic variables once again. This is the tricky part. You have to calculate the non-basic variables coefficients anyways, because they will tell you what values delta can have. So what I have to do is just calculate these values. So as you can see here, minus 2, minus 3 plus delta, minus 5 minus delta, minus 3 minus delta, minus 7 plus delta, minus 2 plus delta. Now, this should remain negative for all values of delta. Okay, how can I make this remain negative? First of all, let's check. This is the positive sign, another positive sign, and another positive sign, and these two are negative signs. So for the positive signs, let's start with the positive signs. If delta is 7, this will become 0. Okay. If delta is 3, this will become 0. And if delta is 2, this will become 0. So delta cannot be greater than 2. Because if delta is greater than 2, this value will become a positive, and we will lose the solution. This is not going to be optimal anymore. So delta has to be less than 2. For positive values, this is pretty obvious. For negative values, minus 5 minus delta, minus 3 minus delta. For this one, if delta is less than minus 5, okay, minus 5 minus minus 5 is 0. So this will become 0. But over here, if delta is less than minus 3, this will become 0. So minus 3 is more constricting, okay? It's more, binding. So we will use minus 3 as our lower limit, as our lower bound. So this says that minus 3 is your lower bound, and this says that plus 2 is your upper bound. So delta should be between minus 3 and plus 2, sorry. So minus 3 and plus 2. Anything between these two will still, any change we make between these two will make sure that we are still optimal. But if this 6 becomes, I don't know, 9, then this will become not optimal. This is going to be suboptimal. And if this is like minus, let's say minus 4, so this becomes a 2, again, suboptimal. We have to change the solution. Okay, how can we change the solution? Let's find the range first, then we can see how the solution changes. So we start with C13. Okay, we are trying to find the solution, the range for this one. 10 plus delta. So we are going to have, we have a u1 of 0 over here. So it's going to be 10 plus delta. This will be 3 minus delta, and this will become 6 plus delta. Then we calculate all the values for non-basic variables over here. So they will be like this one, minus 2 plus delta, minus 5 plus delta, etc. Start with the positive ones, plus delta, plus delta, plus delta, 2, 5, 3. So 2 is my upper limit. What about the minus signs? Minus 3 minus delta, minus 2 minus delta. Once again, minus 2 is my lower limit. So delta is going to be between minus 2 and plus 2. So what happens if I increase this one? Well, let's say that we are increasing this value to 13. Instead of 10, this is 13. Then this one will change, this one will change, this one, and this one, and this one will change. And delta is 3, so this becomes a 1. Okay, if this becomes a 1, I have to find a loop from here. Okay, let's find a loop from here. Let's just annotate and draw. Loop from here. It comes over here, goes here, and goes here. This is my loop. So this will be plus theta, let's say, minus theta, plus theta. So this theta value, 45 to 25, is going to be 25. This guy over here, this basic variable will leave. Well, this is what we were expecting because we have increased its cost to 13. So it should leave the solution. So this one will become a 0. This becomes a 30. This becomes a 20. And this becomes a 25. And hence, this is our next feasible solution. We don't know if it's optimal or not. We will just find the U and V values and keep making iterations if we need to. But still, if we change the delta, let's just do it the other way. Let's say that we are decreasing it by 3. So this value will become a 7. Okay, if we decrease by 3, now over here, this one will become 1, a value of 1. So I have to find a loop from here now. Okay, let's find a loop from there. This is a bit harder to find, but you will see. So start with this one and find a loop. Now I can go over here, but I don't want to. There are 2 options there. There's just 1 option here, so I will just go there. And from here, there's only 1 option. There's only 1 option. There's only 1 option. Another option, and 1 option. Now, again, this is not a rectangle, but it is made of straight lines, and it has corners. So this is a loop as well. Okay, this is important. This is a loop. So starting from here, I go over here, over here, over here, here, and here. Let's count the number of corners. 1, 2, 3, 4, 5, 6 corners. We are good, even number of corners. So plus theta, minus theta, plus theta, minus theta, plus theta, minus theta. Now, this one is getting more, okay? Because its value has gotten smaller, cost has gotten smaller, so it can take on more value over it, which is logical. So this one is the smallest minus theta, which means that the theta is 5. This will become a 30. This one will become a 5. This is going to be 15. This will become a 25, a 5 over here, and 0. And this one will leave the solution. So as you can see, we can find the solution pretty fast, pretty easily as well. All we have to do is just find the loop and make the iteration. That's it. This is easier to do than all those, sensitivity analysis we have made using Java Simplex, for example, and faster, much faster. But this is only a specialized version. This only works with transportation problems, nothing else. Okay, what's the third one? Increasing both supply and demand. So when you increase both supply and demand, you have to check what that supply and demand is, affecting. Is it a basic variable or is it a non-basic variable? This is a simple question. So, for example, we have increased supply over here and demand over here. This makes sure that this part is increasing. Okay, this is increasing, but we don't want to see an increase over here. This is not a good increase for us because this is a non-basic variable. We cannot add a value over here just from our head. We don't want to see it get a value because this cannot become a basic variable by itself. Something else must leave the question for this one to become a basic variable, but it doesn't work. Okay, so if you don't want this one to become basic variable, we have to loop it out of the solution. So find the loop from here. Starting at this point, we have this one. Okay, let's go to 45, 5, 25, and back here. So we should get rid of this one, whatever the delta is. For example, if delta is 5, we have to make sure that this delta over is minus 5. We have to get rid of this one. So we are just taking this delta out of the question. Minus delta, plus delta, minus delta, plus delta. So whatever value has gotten over here should be you know, able to balance this out. So if delta is greater than 5, okay, we have lost the optimality once again. This one will become a negative value. So we will need to find something else. We will need to find a new U and V values and start getting rid of some solution, some basic variables, and find new ones. But still, if delta is a negative sign, if you are decreasing supply and demand, then it can only be at most 25, we would say. But still, over here, you would have to get rid of it at all. So this is always delta minus delta anyways, no problems there. But this would mean that if it's less than 25, minus 25, let's say if it decreased by 30, so it's minus 30, this will become a minus sign, which is not good once again. It will disrupt the objectivity, optimality, sorry, and you will have to make the iteration, find the loop and make the iteration once again. But basically, this is how we work with the sensitivity part. There are 3 different things we can do. We can check for in transportation sensitivity, and they will always be ending with a loop, finding a loop and trying to find a new solution, or if the current solution remains optimal, whether the current solution remains optimal. Now, we also have transshipment problems. Now, these are a bit more complex than transportation problems, model-wise. Once you have modeled them, they are solved the same as the transportation problems, but modeling these problems are a bit harder. Okay, transportation problems are easy because you have a certain number of demands and a certain number of supply points, and you just try to find a balance and solve from that. But in transshipment problems, your supply points can also be your demand points, and your demand points can also be your supply points, or they can be, I don't know, for example, as the name suggests, transshipment points. So, for example, you are sending goods from Istanbul to, let's say, Ankara and Hakkari. Ankara is on the way to Hakkari, for example. And if you are sending stuff to Hakkari, you can stop by Ankara, deliver some stuff, and keep going to Hakkari. So Ankara becomes a transshipment point because Ankara has a supply, but the road doesn't end there. It goes on to Hakkari as well. So you just stop by Ankara and keep going to Hakkari. So Ankara becomes a transshipment point. Or Ankara might have a supply instead of a demand. So you stop by Ankara, take more, let's say, take more goods and bring them all to Hakkari, for example, or vice versa. You can start from Hakkari, go to Ankara, and then to Istanbul. Doesn't really matter. But the point is, any one of your demand points can become a supply point, or any one of your supply points can become a demand point, which will only make the question more complex. So instead of going directly from a supply to a demand, you may have to make, stops, make deliveries or make pickups on the way as well. Now, these are modeled a bit more differently from classic transportation problems, but still the solution type is the same. We use the transportation simplex in that, but we have to make sure that the table is correct. Modeling the table is another story for that one. For example, we have a widget co, which manufactures widgets at 2 factories, one in Memphis and one in Denver. Memphis factory can produce as many as 150 widgets per day, and the Denver factory can produce as many as 200 widgets per day, right? Widgets are shipped by air to customers in LA and Boston. Okay, we have supply points, 2 supply points, and 2 demand points up until now. The customers in each city require 130 widgets per day. Because of the deregulation of airfares, widget co believes, wait a minute. Yes, widget co believes that it may be cheaper to first fly some widgets to New York or Chicago, then fly them to their final destination. So you have stopover points. You have to go over there maybe, and then from there, go to the other destinations. The cost of flying a widget are shown in the table below, as you can see over here. Widget co wants to minimize the total cost of shipping required widgets to its customers. Now, if we just model this with arrows and nodes, we can see that we have 2 supply points, Memphis and Denver. We have 2 transshipment points, New York and Chicago, and both New York and Chicago do not supply anything and do not demand anything as well. They are just stopover points, okay? They just are there to use if we need them. And we have 2 demand points, Los Angeles and Boston over there. So from Memphis, I can go directly to Los Angeles. From Memphis, I can go to New York and then to Los Angeles. And from Memphis, I can go to Chicago, then to Los Angeles. All right. From Denver, I can go directly to Los Angeles. From New York to LA, from Chicago to LA. Once again, the same for Boston. From Memphis, I can go directly to Boston, etc., etc. So for each supply point and each demand point, I have 3 different ways of going there. Using one of the transshipment points or going directly. So I have a total of 6 ways to go from one supply and 6 ways to go from the other one as well. So 3 for each demand point and twice for each supply point. So I have to model this, but to be able to model this, I have to make sure that what paths, let's say nodes, which nodes are my supply points, which nodes are my demand points again. So I already know that Memphis and Denver are supply points for sure. Los Angeles and Boston are demand points for sure. And there are no demands for Memphis and Denver. Why? Because Memphis and Denver do not have any arrows incoming to them. So you have to have an arrow incoming to be a demand point. Even if you don't demand anything, you can be a demand point. Because if you have an arrow incoming there, then you are taking on goods one way or another. If it's for just storage only, it's still taking on goods. You don't need to have a customer there to have a demand there, okay? A storage point can have a demand as well. Same for having an arrow out. So if there's an arrow out of you, you're at a supply point. You don't need to produce anything in there. But if you have a storage point, for example, you have a storage, this is a storage point, a transshipment point is also a storage point. You can think of it like this. If there's a storage point over here, you have goods coming in and then you have goods leaving. So, which means that your transshipment point is both a supply and a demand point, okay? There's an arrow incoming, so it's a demand point. There's an arrow leaving, so it's a supply point. So, when I draw the table, I will put New York over here as a supply point, and I will put New York over here as a demand point as well. So, if I have any goods entering New York, then this is the demand point. If I have any goods leaving New York, then this is supply point. So it can be both a supply and a demand. This is what transshipment is about. And if we said that we could send items from Memphis to Denver or Denver to Memphis as well, they would become supply and demand points at the same time again. And if I said that Los Angeles could send items to Boston if it needed, then Los Angeles would become a supply point as well as a demand point. Okay. So Memphis, Denver, New York, Chicago. These are my 4 supply points. New York, Chicago, Los Angeles, and Boston are my 4 demand points. And I have to add a dummy demand because my supply is greater than my demand. So as you can see, these are my costs. They are just taken from here. Now, if there was a cost for taking the goods to Memphis, okay, for example, if it's a storage facility and they stay there for a day and each daily stay costs $5, for example, then this 0 would have a value of 5 over here. We do not send anything from Memphis to Memphis. This is just the staying cost, okay? So it's still 0 over here, New York to New York, Chicago to Chicago, etc. We do not have anything from Memphis to Memphis because we're not sending anything there. This is a supply point, but for New York and Chicago, these are values of 0. New York and Chicago are the important zeros over here, New York and Chicago, because they are the transshipment points. But still, if Memphis or Denver were transshipment points as well, if they could be demand points, if they had arrows coming into them as well, they would have values of 0 in there as well. Still, this is our table. Now, this table is just a balance table. All we have to do is just find the starting feasible solution, a basic feasible solution, using any method we want, then find the U and V values. We have seen how to do that half an hour ago, and then use those to calculate if this is an optimal solution or not, and then find the optimal table, which is like this for this question. Now, up until over here, everything is a bit more different, but when you come over here, when you have the table, it's just a transportation simplex. It gets back to the beginning once again. So what we have to do is just from the question, find the table. Okay. To find the table using nodes and arrows is the easiest way. This is, finding the table for a transshipment problem is a bit more complex than a normal transportation. So try to use those nodes and arrows to make sure that you can see everything and you don't miss a transshipment point. And then you can just take it over here. Now, for example, we have another example over here. This is a Sanko oil example. Now, in this oil example, we have, let's take a look. These are our supply points. These are our demand points. Now, well 1, well 2, there are 2 wells, okay? And there is Mobile point, okay, Galveston point, New York point, Los Angeles point. So there are 4 transshipment points. They also have demands as well. Oh wait, I missed something. In the table, I should have talked about supply and demands over here. Let's go back. Memphis, let's say, has a supply of 150 and Denver has a supply of 200. So I will just write those over here, 150, 200. So we know that these arrows should equal to, all these 4 arrows should equal to 150. And all these arrows going out of Denver, these 4, should equal to 200. That's cool. And all these arrows entering Los Angeles, okay, they should be 130. And all these arrows entering Boston should be 130 as well. This is why we have a dummy for the excess supply point. But still, we know that Los Angeles and Boston have a demand of 130. Memphis and Denver have supplies of 150 and 200. That's cool. What about New York and Chicago? Okay, as you can see, New York and Chicago have supplies of 350 and demands of 350. Why? Okay, we know that they don't produce anything and they don't demand anything, but they should have demand and supply values, and it's 350. Why is it 350? Well, simple. For New York, the maximum amount of goods it can have is 350. Why? Memphis can send all of its 200 over here, and Denver can send all of its 150, or the other way. Yes, Memphis can send all of its 150 goods to New York, and Denver can send all of its 200 values to New York as well, goods to New York as well. So New York has 350 to distribute to other, cities. So it can just distribute whatever it has to other cities. So the maximum number of goods New York can have is 350. This is both correct and incorrect as well, because we have a dummy of 90. So we already know that we will never send 350 to New York or Chicago, because this dummy will never be sent. So actually this is 260, but you don't need to think about it. You can leave it as 350. It doesn't really matter. It's easier that way. Just take the whole supply and write it there. Because if you don't take this as 350, you may make a mistake. Okay, in a more complex situations, if you try to find the absolute minimum value this one can have, these transshipment points can have, you may miss something and get a lower value than needed, and you may make a huge mistake there. So taking this one, a greater value, doesn't change your solution. It doesn't impede your solution. These values can be 500 if you want. If these are 500, then you will still find the same solution. It won't matter. Because, for example, when we have find the solution, as you can see, there are 220 units being sent from New York to New York and 350 units being sent from Chicago to Chicago. This means that Chicago is not using its capacity of 350. So we do not have anything coming into or going out of Chicago, because 350 out of 350 is used on itself. We have 220 used on New York, from New York to New York. This means that this capacity of 220 is not being used for New York, but the rest capacity, 350 out of 220, which is 130, is being used in New York. So New York is not using 220 of capacity. If this value was 1,350 instead of 350, this value would become 1,220. Still the same thing, with a value of 0, with a cost of 0. This will not change anything. This is like the artificial variable, okay? But or a dummy variable, something that can have a positive value, but it doesn't change the solution at all. And over here, 350 units with a value of, with a cost of 0. It doesn't really matter, okay? These can have any value depending on how you choose those supply and demand points. But choosing them as the total supply and total demand, or when on one of them, is the easiest way, okay? But usually go with the greater value to make sure that you do not make any mistakes. This might, make you use or make calculation with bigger values, bigger numbers, but doesn't really, slow it down. It won't really slow it down. It doesn't really matter. So as you can see from here, we have dummy values 20 and 70. These dummy values mean that Memphis, out of its 150 supply, is not producing these 20 units, and Denver, out of its 200 supply, is not producing these 70 units. So they don't need them. And from here, this is the Sunco oil question. Now, here some things are different. Now, with the Sunco oil, New York and Los Angeles cannot send to mobile or Galveston. So these are M values, but New York and Los Angeles can send to each other. So as you can see, New York and Los Angeles are actually demand points, but they can send each other. If I try to, let's say, draw this one, I'd probably say that, okay, I have two wells over here, well 1 and well 2. I have mobile and Galveston, they are transshipment points. They look like transshipment points, at least for now. And I have New York and Los Angeles over here and over here. Now let's say that we'll just use the, yes, this one. So from well 1, I can send anywhere. So this can go like this or like this, or these two can go like this or like this. And I can have, let's find an arrow over there. No, we don't have that one, right? No, I can just, I can go from here to here and here to here. And this looks ridiculous, but still nothing I can do about this right now. So, and I can also send from mobile and Galveston to each other. As you can see over here, mobile can send to Galveston and Galveston can send to mobile. So we can go like this or like this. And these two can send to each other as well. And these can send to the finishing points. So as you can see, these two demand points can also send stuff to each other, but it cannot send back to other places. So New York and Los Angeles cannot send back to mobile or Galveston, and well 1 and well 2, these two wells are not even taking anything, so they cannot be in the demand points, so they're not even in the list over here. So these two can send to each other. From here, this is again a balanced solution, a balanced table, and all I have to do is just run the transportation simplex. So the question itself, the sunk oil question itself, is something like this. We have two wells producing oils. We have to send them to mobile or Galveston, and from there we can send them to Los Angeles or New York. But we don't have to use mobile or Galveston. They are just transshipment points. We can send direct to New York or Los Angeles as well. But when we, solve the question using this node zero and using, of course, this table, we find something different. But still, from here, we have to make sure that if there's any sort of question, any sort of, let's say, change, something like, okay, you have to stop by mobile or Galveston. If you stop by them, you have to, refine them as well. And after refining them, you can send them on to New York or Los Angeles. Then this changes the question. For example, you have to make sure that you have to refine them on mobile or on Galveston. Then you have to add something different. You have to add some, new demand points, which will become something like, let's just get on to the next one. Something become like this. Because now take a look over here. We have mobile unrefined and mobile refined, mobile Galveston unrefined and Galveston refined. What's going on here? Now we are sending oil from well 1 and well 2 to mobile and Galveston only, because there's a refinery there on both mobile and Galveston, and we have to make sure that this oil is refined and then sent over to New York and Los Angeles. So mobile and Galveston are not only transshipment points now, they are also operation points. Something is happening on the goods there. Okay, they become supply points in a flash. Suddenly they are supply points as well, and they are demand points as well. We have to make sure that anything that comes out of the well goes into mobile or Galveston. So to be able to model this, we have to make sure that there is an unrefined part and a refined part over here, because this might be, for example, when you refine oil, it becomes gas, for example, and when it becomes gas, it loses quantity. Okay, this might happen, or it gains quantity. This might happen as well. I don't know how refinery works over there, but still, the quantity might change. So we may be supplying barrels of oil, and we might be trying to get barrels of gas, and barrels of gas might be less than barrels of oil. Okay, what happens there? When we get unrefined stuff in there, it becomes refined. It might change or might not change. We don't know yet. But still, if it doesn't change, if it stays the same, this is good for us because we can use the transportation easily there. But if it changes, it will complicate things. So we don't need to go there yet. So from well 1, I can only send to mobile or Galveston, and they will be unrefined parts. Okay, I have to make sure that we get unrefined stuff for them. Why? Because after I send, for example, oil to mobile, from unrefined mobile, I can send them to refinery so that it becomes refined oil, or I can send them to Galveston unrefined as well, so that it becomes refined in Galveston. Now, this is important because the operation itself is costly as well. As you can see over here, it's 12 for mobile. Let's see, Galveston is 10 for Galveston. The operation itself is costly over here. So from mobile unrefined, I can do the operation here and refine the oil and turn it into gas, or I can just send it to Galveston to be refined. So mobile can act as a transshipment point and take all the oil to Galveston, or mobile can act as a refinery as well. It can happen. Okay, both can happen. And from unrefined, I cannot send to New York or Los Angeles. New York and Los Angeles only accept refined oil, okay, the gas version. So from mobile refined, I can send them to New York or Los Angeles. So from Galveston, again, unrefined, I can only refine it, or I can only keep it. I don't have any other options. So Galveston cannot be a transshipment point because it doesn't send anything to mobile over here. Mobile is a transshipment point, but Galveston is not, because it doesn't accept. It's actually a transshipment point because it accepts from well 1 and well 2, but it's not a transshipment point when compared to mobile. Okay, it doesn't accept anything from mobile. Okay, it's an operation point only. So Galveston can get unrefined oil from well 1, well 2, or mobile, but it cannot send anything to mobile. Okay, it can only send to New York or Los Angeles after it is refined, as you can see. So it can also send to mobile refined, it seems. Galveston only can send to mobile after it has refined oil. It cannot send unrefined oil to mobile, it seems. So if New York is the, by the way, final point, as you can see, there are no other Los Angeles over here as well, but New York can act as a supply point as well. So it can send stuff to Los Angeles, for example, but we don't know the demand points. So you have to calculate them by yourself, and you have to make sure that you check the supply, total supply, so that your total demand is the same for that one. Okay, this is a bit more complex. We have to go over it a few times, but the Sanko oil's original question can be found in your book. I don't know why I haven't put it over here, but it's a simple question made more complex by adding this refinement part. But still, this is the most complex you can find in a question as well. Okay, it doesn't get more complex than this, even in the exam. You will see in the finals anyway, something like this probably, but it will not get more complex than this one. Trust me on that one. So this is how it happens with refinement parts. So let's take a break now. Now, in this table here, you can see dummy demand for a specific supply point. Now, this is something about the modeling part. For example, just think that you have a supply point and you can send goods via 2 different paths. Okay. For example, you can say that, okay, I can send them with, I don't know, air, by planes, or by trains, or by trucks, etc., by land. So you can have 2 different ways of sending the same, supply from 2 different paths. Now, you do not know which path you will use. It can be by air or by land or something entirely different, but you do know that your total is 50. Okay, your amount of goods is 50. So you can either send all the 50 via path 1 or all of them via path 2. So all of a sudden, your total output becomes 100, which is not possible. Your output is 50 anyways, but with 2 different paths, you could have said it would be 100. Now, at this point, we have to create a dummy supply point or dummy demand point for that supply point, like this one. Now, this dummy, this dummy demand for the supply one is going to take the excess, goods, the goods that are not really there, that you're not sending anyway, and it will say that, okay, your path 2 is not doing anything. You are sending everything through path 1. So this supply only works, this dummy, sorry, only works with supply 1. It doesn't work with supply 2. So its cost is going to be m, an infinitely large value or something big enough, so that you will never assign any values over here. And these values will be whatever zero, the cost will be zero, whatever you need to, keep it there. But still, when you go back here, you can see that, okay, supply 1, path 1 sends 50 units to demand 2. Supply 1, path 2 sends nothing to demand 1 and sends 50 to dummy 1. And as you can see, there is 0 over here. Now, what about supply point 2? Supply 2, path 1 sends 40 to demand 1 and 10 to demand 2. Nothing goes to dummy 2, and everything from supply 2, path 2 goes to dummy. So these dummy points are only assigned, are only created for these specific supply points. Okay, they are not universal. They are not all encompassing. They are just for this supply point, so that this total will not be 100. This total will stay at 50. Item sent, really sent, will stay at 50. And this dummy of 50 will be subtracted from this total. So as you can see, this 50 negates this 50. So this is not being used. This is unused path, okay? And as this is an unused path, everything is sent from here, and this 50 is the produced real number of goods, okay? And same over here, 40 plus 10, 50 is the number of real produced goods, and this 50 is not produced, it's not there. It's artificial, okay? It's not real. So you can assign dummy demands or even dummy supplies to specific, supplies or demands. So this dummy demand is set for the first supply, okay? And this dummy demand is set for the second supply. You cannot have any values, any other values for that dummy. Only for supply 2 and only for supply 1 in this column. So this is about everything about for the transportation and transshipment problems. What about assignment problems? Now, these are even more specialized versions, because with transportation, you had supplies and demands and their values, 50 supply per supply point, 20 demand for demand point, etc. With assignment problems, every supply and demand is just one. You don't have any supply and demand actually. They're all one, okay? Because you are trying to assign some stuff to other stuff. So once they're assigned, it's done. It's just pairwise assignment, that's it. You're not producing anything. Or even if you are producing anything, you're just assigning factory to city. That's it. You don't know how much you will send. You don't care about that one. You just know the cost or quality, depending on the assignment type. And you know that you can assign those to others. That's it. Now, this is done with tables, just like transportation problem, but it has its own solution method. You don't need to use the transportation simplex and vogels and stuff like that. You can just, you could do that, by the way. You could just give supply and demands values of 1, and you can just use transportation simplex and whatever you wanted to, but there's an easier method. So it's called the Hungarian method, Magyar yöntemi in Turkish, and we use that method to easily and extremely rapidly calculate how the assignment is made. Well, first you have to start with finding the minimum element, minimum value, because it's a minimization once again, and find the minimum cost and then subtract that cost from everything in that row only, and do that for all the rows, and then do that for all the columns, and you will get some, subtracted values, subtracted cost in there, and then from there you have to try to find the 0 values. You will have some cells with values of 0 and cancel those zeros with lines, okay? Draw them out with lines. And the number of lines should be equal to your number of rows or columns. Now, as this is an assignment, this is going to be a square table. It has to be a square table every time. You cannot have 4 rows and 3 columns or 5 rows and 10 columns. It has to be 2 by 2, 3 by 3, 4 by 4, 5 by 5. Nothing else can happen because it's assignment. It's a pairwise assignment, one-to-one assignment. You cannot have anything else. Always a square. So you try to draw out those zeros with the minimum number of lines possible, straight lines, of course, possible. And then you count the number of lines. If those number of lines is equal to your number of columns or your number of rows, that's the same thing, then you have found the optimal solution. But if it's not, you keep going. Now, if it's not equal to the number of rows, then you need more rows. To be able to find them, you check whatever is left with whatever value that is not, drawn by a line, and find its minimum value, and take that minimum value and subtract everything that was not drawn once again by that value. The example will be easier to understand, but this is just a talking part, let's say. And then at the same time, you find every cell that was crossed out by two lines, okay, one horizontal, one vertical, and then you add that value, that minimum value, to those points, to those cells. You will see what I'm talking about. So for example, we have 4 machines and 4 jobs, and these are the number of hours it takes to complete that job on that machine. So we are trying to minimize the total hours spent doing those jobs. So we are trying to assign jobs 1 to 4 to machine 1 to 4. And each job can only be assigned to one job, and each machine can only take one job and one job only. So we will take these costs and turn them into this table. Now from here, we start by finding the minimum values of each row. So first row, the minimum value is 5. So I will subtract 5 from everything over here. So 9, 0, 3, 2. Second row, minimum value is 2. Subtract everything, subtract 2 from everything. So 0, 10, 4, 3. Third row, minimum value is 3. So subtract everything, 3 from everything. So 4, 5, 0, 6. Fourth row, minimum value is 2. So subtract 2 from everything. So 0, 2, 4, 8. Now, go back to the state and start with taking the minimum values of the columns. 0, no operation, 0, no operation, 0, no operation, 2. So subtract 2 from everything, 0, 1, 4, 6. Now, as you can see, this is the current table. And in this current table, what I have to do is just find the zeros. So I have 0 over here, 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 and here. 1, 2, 3, 4, 5 zeros. And just, remove those zeros with lines. So I have 2 zeros in this first row and 2 zeros in this first column, and 1 zero in this third row or third column, depends on me. So I will just strike out these first and row and column. So I have gotten rid of 2 zeros at once with just one strike, just one line, which is good. Then I will just strike out this third row. So 1, 2, 3 lines to get rid of 5 zeros, which is good. But I need 4 lines. As I have been able to find the minimum value of lines I need is 3. This is not optimal. So what I'm going to look for is the minimum value in these leftovers. So 10 for 1, 2 for 6. 1 is the minimum value. So I will take this one and subtract it from everything that is not crossed over. Okay, so 10, 4, 2, 4, 6, and 1. Subtract 1 from all of them. 9, 3, 0, 1, 3, 5. And add this one to any cell that is crossed over twice. So like this 9 crossed over twice, and this 4 crossed over twice. Add 1 over here. So 10 and 5. Nothing else will change. So now I have a 0 over here as well, another 0 over here. So 1, 2, 3, 4, 5, 6 zeros. Now I need 4, strikes, 4 lines to cover all the zeros, which means that I have reached an optimal solution. So I will remove those lines and see all the zeros over here. I will have to pick 4 zeros that covers all 4 columns and all 4 rows, so that I will find the optimal solution. To do that, check the unique zeros in each column and row. For example, in the first row, there are 2 zeros. I cannot pick between them. In the second row, there are 2 zeros. I cannot pick between them as well. I'm not sure which one is going to be, assigned yet. But in the third row, there's only 1 zero. So this is for sure an optimal point. So this is picked. In the fourth row, there's another 0. So this one is picked as well. Once I pick a number, 0, I will have to cancel out its row and column. I will not use these anymore. And same for here. If I pick these are gone as well. Now, with these all gone, I have only 1 0 left in the second, row I can use. So I will pick that one and everything else will go. And this row is left alone. So this is the last assignment. So as you can see, 1, 2, 3, 4 assignments. This says that I will assign, I think, let's go back and see, to the left was the machine and top was the job. So the second job is assigned to the first machine. The first job, this one, is assigned to the fourth machine. The third job is assigned to the third machine, and the fourth job is assigned to the second machine. And their values were 5 over here, 5 over here, 3 over here, and 2 over here. So the total time it takes is 15 hours. 5 plus 5 plus 3 plus 2. You cannot find a better solution than 15 by selecting 4, assignments in here. Once again, you cannot just pick this 2 and this 2 at the same time, because there can only be one assignment per row and per column. That's it. So this assignment is the best one. These 2 zeros are not important right now because they cannot be picked anyways. So this is the solution. Okay, but this is just a simple version. Let's get a bit more, harder. For example, 5 workers are available to perform 4 jobs. Now this means that I have 5 workers and 4 jobs. This is not a square. I have to make sure that it's a square, so I'll get there. The time it takes each worker to perform each job is given in the following table. Times given are in minutes. 2 dashes refer that the job cannot be done by the worker. So it requires some certain skills and it cannot be done by that worker. The goal is to assign workers to jobs so as to minimize the total time required to perform the 4 jobs. So it's a minimization once again. Use the Hungarian method to solve the problem. Okay, these are the 5 workers and these are 4 jobs. So this means that one of the workers will be unassigned. He will just stay out or she will just stay out. So I have to create a new job for that one, a dummy job, which means that, okay, this guy is outside. Okay, he is waiting out. He's not doing anything. So I have a dummy job, and this dummy job can have any value. It might be 0, it might be 30, it might be 100, it doesn't really matter because the dummy job isn't important to us right now. We will just say that, okay, the greatest value is 30. Let's give a value of 30 to the dummy job. But I could have given it as 0 as well, but I will not give it as 0 because I want to make sure that there are rows I can operate on. I don't want to see a 0 at the beginning. And for those 2 dashes, they have values of m. They cannot be assigned. Okay, I can just say m to them. Okay, these have m values, and these are values of 30, the greatest value on the table. I could have assigned 0 to them. It wouldn't change anything. I would just not be able to make any row operation at the start because all rows would have a minimum value of 0. I didn't want that, so I have given them a value of 30. So what is my smallest value over here? 18. Another 18, so 20, 14, and 21. Just subtract everything. I will get these values and take a look at the columns as well. 0, 0. Okay, 4, 0, and 9. So subtract those as well. I get these values. Now from here, I can see that 2 zeros over here, 2 zeros over here, 2 zeros over here, and 1 zero over here. I'm just going to use all the lines upside down for columns and strike the zeros out with 4 lines only. So I need another 0, which means that I'm just going to find the lowest value over here, which is 4. So I will just use that 4 to subtract everything from that unmarked ones, unstruck, whatever. Unstruck ones. So this 4 is going to be subtracted from every value over here. M will never change, by the way. Even if I subtract something from m, m is still m. It doesn't really matter. We don't make any operations on m. So this is another 0. But I can still use 4 lines to strike out all the zeros. Surprise. So I have to get rid of more values. I'm just going to take a look over here and here. The smallest value is 1. So subtract 1 from everything and add that 1 to 2 crossed cells. So this 0 will become a 1. Now we are getting rid of a 0. It's important because sometimes this can happen. This 0 wasn't really a 0, it seems, because I could have gotten rid of it. So it will become a 1, as you can see over here. Now I have 1, 2, 3, 4, 5 lines. I cannot find anything to cover all the zeros with less than 5 lines. So this is the optimal solution. I have to pick which zeros I can use. So let's take a look. This is the only 0 in this column. So I will use this one. It's cool. So when I use this one, I'm getting rid of, let's just draw them. I'm getting rid of both these column and this row. So let's check this one. This 0 cannot be assigned because this is not unique one. This 0 is unique for this column once again. So I can assign this 0 and I'm going to love these 2. And this 0 is unique for this row. So I can assign this 0 and get rid of these 2 columns. This 0 is unique for the dummy job, so I can assign this one and get rid of this one. And this is the remaining 0, so I will just assign that one as well. So as you can see, all the red zeros are assigned. So my first job is assigned to my second worker, my second job is assigned to my first worker, and the third worker is staying out. On the dummy job, it's not working. The fourth worker is doing the fourth job, and the fifth worker is doing the third job. So all jobs are assigned to a worker except the third worker, which is assigned to the dummy job. So it's just not working today. This is how the assignment problem is done. One more type, which is extremely important. Let's say a company has 3 machines to assign to 4 different jobs. Any one of the machines can do any 2 of the jobs, but when a machine is assigned to the 2 different jobs, the second job loses 10 points of quality. Now, this is a bit more complex because I have 3 machines and 4 jobs, and I can assign 2 jobs to a machine. It allows me to assign 2 jobs to a machine. So I have to find a way to assign 2 jobs to a machine. Okay, but it also says that if you assign a second job, it loses 10 points of quality. Okay, the machine job quality values are given in the table below. So as you can see, there are 4 jobs and 3 machines. So if I assign job 1 and job 2 to machine 1, and say that second job is the job 2, then this one will lose 10 points of quality, which will mean it will have a quality of 15 instead of 25. And these are maximization objectives because this is quality. I want to maximize the quality, but all I have seen is minimization up until now. How am I going to deal with this? And we will see. First, let's try to find the table. Then we will deal with the maximization part. So how can I create a table for 4 jobs and 3 machines where I can assign 2 jobs to a machine? Well, I will just say that I have machine 1, okay, and machine 1 can do 2 jobs. So job A and job B. I can just say that M1 and M1B. M1 is going to be the first job assigned to machine 1, and M1B is going to be the second job assigned to machine 1. I can do this for all 3 machines. So I will have M1, M1B, M2, M2B, M3, M3B, 6 rows. So I need 6 columns as well, but I only have 4 jobs, which means that I will have 2 dummies. Dummy job 1, dummy job 2. These are going to show me which machines don't have second jobs. Only 1 machine will have a second job because I have 4 jobs and 3 machines. Only 1 of them can have 2 jobs. Maybe more of them can have 2 jobs. 1 machine can sit idle and 2 machines can do 2 jobs, but still there is a pattern to it. There's a way to it. So I need 2 dummy jobs showing who is sitting out this one or who has just 1 job and no second job. So what I have to do is just create 2 dummy jobs. These are my dummy jobs, and they have qualities of 0 because they don't affect the quality of the job. So they will just remain like this one. But in here, this is a maximization problem. So to get rid of this maximization problem, I have to make this a minimization problem. All I have to do is just multiply everything here by a minus sign. So I have minus 45, 44, minus 25, etc. Everything is a minus over here. So let's start by getting rid of these minuses because I have to make sure that there are zeros in here. And what I have to do is just start with finding the minimum value of the row, which is minus 44, and subtract minus 44 from everything in the row. Well, that's easy. This is 0, this is 19, 7, 5, 44, and 44. Because if I subtract minus 44 from 0, it's plus 44. Same thing from here. The least, the minimum number, the minimum value, minus 35. Subtract minus 35 from everything over here. Minus 48, minus 34, minus 25, minus 38. Subtract them all. So you get this table. Now, at this point, everything is as it seems as we needed it, as we needed to see it. So we just go, on from here. We have gotten rid of the rows, so we need to check the columns. This is the normal Hungarian method now. So zeros. We have 4s over here, 3s over here, and let's check over here 25 and 25 over here. So just subtract those numbers. So we have gotten lots of zeros, but only 3 lines covers all these zeros. So what I have to do is just find these values, the minimum of these values, which is 2. So subtract 2 from everything in here. 2 zeros added, so 4 lines. Still not enough. And I have added 2 over here to these points over here, as you can see, 4 and 4. So with 4 lines, the minimum value is 1. So subtract 1 from any uncrossed value, and add 1 to double cross 1. So these zeros will become 1s as well. We are getting rid of zeros as well over here. So now I have 1, 2, 3, 4, 5 lines. Still not enough. I need 6 lines. So find the minimum value and get rid of those, subtract that minimum value from any uncrossed lines and cross marks, and add it to any double crossed points. So 5, 0, 0, 5, and 1 and 1. These 6 values will be added. These 6 values have 6 added over to them. So 1, 2, 3, 4. Again 5 lines. Still not enough. So find the least value over here, which is 2 and 2. Subtract those 2 from every uncrossed, unmarked values and add it to every double crossed one. So this is the last table. We have 6 lines over here. So with 6 lines over here, I'll just have to check which zeros I'm going to use. Now, there is, let's say, if you take a look over here, there is actually no zeros, I think, that is left alone, right? So everything in here, everything in this line has 2 zeros, 2 zeros, 2 zeros, 2 zeros, actually 4 zeros, 4 zeros, and 2 zeros. Over here, 2 zeros, 2 zeros, 4 zeros, 4 zeros, 2 zeros, 2 zeros. No unique values. Okay, what does this mean? If there are no unique values, can I even start, assigning? Yes, I can. I can just pick anything I want. It means that there are alternative solutions. Okay, how? Like this. For example, if I assign any one of them, start with any one of them over here, this says that dummy job 1 and dummy job 2 will be assigned to M1B and M2B. So I'm pretty sure that the third machine is going to have 2 jobs to complete. So all I have to do is just start with the third machine. Okay. Now this is very important. If I start with first or second machines, I can make a mistake. But the third machine, well, it will already have 2 jobs assigned to it. So I can say that third machine can have job 1 and job 2. So I don't care which one is A job and B job. Okay, there are 2 jobs, job A and job B for the third machine. I can have job 1 as the A job and job 4 as the B job, or I can have job 1 as the B job and job 4 as the A job. Doesn't really matter, but job 1 and job 4 are assigned to M3. This is certain. So I can have these 2 zeros or these 2 zeros over there. Doesn't really matter. So it seems we have assigned job 1 to machine 3 and job 4 to machine 3 as the second job, job B. When I assign these 2 zeros, I'm getting rid of lots of zeros anyway, but it doesn't really change anything for me. I'm going to have to still find the best value I can assign. So let's keep going. If I assign job 2 to machine 2, I can assign it over here or over here. Well, I prefer assigning it over here. This is better because I wouldn't want to assign the job to machine 2 as the second job because I know that it will lose quality. It doesn't show it over here, but I know that it will lose quality. And I know that I have to assign job 2 to machine 1 at that point. So, because I cannot assign job 4 anymore because I have already assigned job 4, so I have lost this column. So this will be assigned to machine 1. So this one will go away. So this one will be assigned to machine 2 anyways. And the B jobs will be the dummy jobs because there are no dummy jobs available at all. So I can assign it like this or like this. It doesn't really matter. As I said, alternative solution. You can assign it like this or like this. Doesn't really change anything. Same for machine 3. You can assign it like this or like this over here. It doesn't really change anything because they are just alternative solutions. Let's go back and understand it from the first table. We know that we are going to assign job 1 and job 4 to machine 3. So if I assign it job 1 to the first job as first job, it's going to get 48, and the fourth job will get 31. The total is 79 quality points. Cool. If I assign job 4 as the first job, it will get 41, and job 1 as the second job, it will get 38. Total is 79 again. Same thing. So alternative solution. It doesn't really matter which you pick. 48 plus 31 is 79. 41 plus 38 is 71 again. Okay. It doesn't really matter which one is the first and which one is the second for this problem. It might have differed in different problems, but for this one, it doesn't really matter. So let's keep going, and we get this, solution at the end. And as I said, this can have alternatives in it. And this is again one of the more complex assignment problems. You will not see anything, weirder than this one, hopefully.